Topic Notes 2.4, Marine Aquariums. This is where we're going to apply some of the chemistry we've learned and look at how it reflects in natural systems. This picture is from the Georgia Aquarium, which is one of the largest aquariums in the world. The particular tank that this is a picture of is the Ocean Voyager exhibit, which is a little over 6.3 million gallons. It contains whale sharks, which are the largest fish in the ocean, literally, even though they're a shark. And they do feed on some of the smallest, mostly plankton and krill. Now, if you look at this picture, you can't even see the back of the tank. It's a massive system with so many marine life in there. It's incredible. How do you maintain such a system on such a large scale, but also on a small scale like the tanks in our academy right now? That's what we're going to focus on today. Now again, these significant ideas today really focus in on the same thing we've been talking about for a while, the chemical properties of the ocean and how that affects the marine environment. And in this case, we're going to use aquariums to kind of show a mimicking of the marine environment and how these cycles really work. And of course, in terms of our learning goals, we're going to try to apply the concepts of chemical oceanography that we've already learned to the maintenance of these aquariums and be able to list some of the different types of filtration we use in the marine aquariums and relate each type to the natural processes in the ocean. Now, first up is pH. Now, we've already talked about pH in the carbonate cycle and how that works. So we know that the pH of the ocean is somewhere in the, in marine aquariums, we generally will keep the pH between 7.8 and about 8.4, kind of within that realm, which mimics many ocean habitats out there. Reef tanks tend to have a requirement. They have to be a little bit more on the upper end of that spectrum. Fish tanks in general without any major invertebrates tend to be a little lower, but they tend to be in that zone. So for a normal pH to occur, there has to be some maintenance because there's a trend for pH to continually go down, to become more acidic over time in an aquarium. So why does the pH decrease over time? Well, mainly it's because acids build up. Remember, acids release hydrogen ions and thus increase the acidity, decreasing the pH. Well, first of all, excess CO2 will do that. So if you have a lot of respiration going on, that can cause a change in the balance and decrease your pH. Also, nitric acid forms through biological filtration processes, and that does add to it to a small degree as well. And then if you have organic acids from metabolic waste, all these things will eventually continue to decrease that pH over time. Now, this is the same thing that happens in the ocean. So how is it actually countered? Well, if you remember from our discussion of pH in the carbonate system, there is a natural buffering tendency in the ocean that helps maintain the pH. Really what this means is you have sources of carbonate and bicarbonate, and this helps to soak up some of those extra hydrogen ions and get them out of solution, thus increasing your pH back up to, above 7.8. In the ocean, there's kind of an endless source of carbonate and bicarbonate from rocks and sediment and all that sort of thing. In a marine aquarium, we're kind of a little isolated. This will be sort of a trend that we'll look at because we're in such a small confined space. We have to provide carbonate from time to time into an aquarium. Now, most aquariums that are reef aquariums have a type of sand, an aragonite sand, and they have rock in there that's usually some sort of limestone base, and that all provides a lot of carbonate as is. But eventually that will start to get used up, and you might need to add some new substrate in there to help boost that out, and the bag of crushed coral there is an example of that, or buffering powder, which is basically a carbonate powder that you throw in the water, and that helps do that job as well. So these are things we have to monitor in a marine aquarium by regularly testing the pH and making sure the balance is okay. And when you start to see the balance skew low, then you need to do something to improve that. Now, of course, another method is also to do a water change, because water is holding a lot of those acids as well, and that will help change things out. But you really want the system to be self-sustaining as much as possible. We started off our discussion with pH. Now we'll move to actual filtration. But first, why do we filter the water? Well, if you're containing an animal, a fish, invertebrate, in a small enclosure in water, it's going to be going through its normal biological processes. Otherwise, meaning they're going to go to the bathroom. They're going to produce ammonia in the case of a fish, for the most part. Now, that ammonia is pretty potent, and it's going to start to build up in the tank if something doesn't take it out. It would be kind of like you swimming in your own urine all the time. It's not only not pleasant, it's also toxic, and it can kill the fish. The other thing that builds up is the DOC, or dissolved organic compounds, and these are like proteins, carbohydrates, lipids, things like that. All of this stuff starts to build up in a tank, and it will start to feed things that are unwanted, like cyanobacteria growth, which is that picture on the bottom right, or other types of algae that will grow and make an imbalance in the system. And if there is an imbalance, you're going to start to see side effects. The color of the water is going to get a little yellowish, and it's going to smell a little bit. It's going to become toxic and dangerous for the fish or the invertebrates that live there. So the ocean has its own natural cycles that tend to take care of all this stuff. And of course, it's a lot larger scale. You know, the ocean is a huge volume. A marine aquarium is a very small confined space. And so things can go wrong in a very small space where it is a little bit more difficult and a little easier to manage on the scale of the volume of the ocean. But the actual methodologies and the systems that are in place to take care of these waste products are the same either way. So there are three major types of filtration that we're going to talk about: mechanical filtration, biological filtration, and chemical filtration. Now, we employ almost every one of them in most aquariums to some degree or another. And of course, you get really high-tech aquariums like the one pictured here with all the clicks and whistles. And then, of course, you have ours, which are a little bit less. But they pretty much rely on the same principles. So we'll start with mechanical filtration. Now, just as the name implies, this means you're going to physically remove particles from the water. Pretty straightforward, and there's a lot of ways to do this, but generally what you end up doing is pushing water through some sort of filter media. This can be something like the overhang filters you see here on the bottom right that have filter pads in them, like the bottom left, where it's pushing water through that filter pad and then particulates get caught in it. We also do that in wet dry filters where the water comes down off the tank into the sump and it runs through a filter pad first. So pretty straightforward. They do clog easily. You do have to clean these regularly, but it's there. And mechanical filtration does occur in the ocean as well if you think water is constantly moving around and sediments and particulate are falling out of solution. Those types of things do happen a lot. However, even though it's an important thing, it's really one of the least important parts of the filtration systems that we actually rely on to keep the aquariums going. Biological filtration is by far the most important type of filtration that we'll deal with, and it really happens in nature all the time. First of all, every surface in a tank and in the ocean is covered with bacteria. Now, you might think, oh, that sounds horrible, oh, nasty bacteria, but bacteria are really good. They make the world go round in a lot of ways, and in an aquarium, they're critical. We wouldn't be able to run aquariums without them. So what do? Well, those bacteria break down ammonia and nitrite, which are the products of fish basically excreting waste, and they're toxic chemicals. So the bacteria break those down into nitrate, which is less toxic, and that is huge. It's really, really important. So all the rock you see in a tank is critical because it has all that bacteria. all the sand and substrate in a tank is really critical. It has all that bacteria. And underneath, the wet-dry systems and the sump systems that we have what we call either bioballs or even more rock or whatever media we want to put down there, and they all hold bacteria. So we're really trying to culture a lot of this nitrifying bacteria so that it's going to help take all that ammonia, that toxic, deadly stuff, and turn it into something that we can deal with, nitrate. So this is the point at which I'm going to talk a little bit about the nitrogen cycle, which is a biogeochemical cycle that we're going to get into in a little bit more depth later on in the course. For the purposes of our talk today, this diagram will do it. So you have fish producing ammonia through waste products, right? They do that because they're eating food, organic matter, whether it's algae, whether it's food you put in there, whether they're eating little copepods that are flying around in the tank. Either way, they're digesting things, they're going through cellular respiration, they're producing waste products, ammonia comes out. The bacteria take that ammonia and turn it into nitrite, which is still a little toxic, but it's still good. Both the nitrite and the ammonia can actually be soaked up by the algae, but that's a whole nother story. From there, the nitrite is converted to nitrate. Nitrate, again, is less toxic, but it's still there. And again, algae can actually feed back into this, and thus it can actually go back to the fish that way if they're eating the algae. So there is a cycle that goes on here. This is not unlike what happens in the ocean. Once again, these things are natural occurring cycles. Now, that nitrate does hang out and start to build up in the tank. There's really nothing that's taking that out unless you do a water change, and that's part of the volume of the ocean. You don't have to worry about this so much. There's other parts that take that out, but when it comes to a tank, it does build up. So that's why you need to do about a 20% water change every month to try and take that out of the system and put fresh water in. But if it wasn't for that bacteria, we would have no ball game whatsoever. This would not be occurring. So bacteria are amazing and awesome in a marine aquarium and in the ocean in general. So chemical filtration is our next type of filtration, and it is very useful, especially if you have a almost purely fish tank with very little bacteria bed. If you have a full reef system, there are types of chemical filtration to use, but not as much. And so what really we're talking about is trying to get out the dissolved components that you really can't get out through mechanical means. And we generally use things like carbon. Carbon in granular form will have a high surface area, and it will absorb a lot of these heavy metals or dissolved organic compounds and help clean the water. Now, if you're doing this in a reef tank, it's kind of bad because not only is it taking out the stuff you don't want in the tank, but it's taking out the stuff that you do want in the tank, like some of the trace minerals and vitamins and things, calcite and things like that you do want in the water for your corals or your invertebrates to grow. So in a healthy reef tank, you shouldn't be using stuff like carbon. And there are a few other absorbing materials that are targeting phosphates and other things like that. But that's something you need to consider. Now, in the open ocean environment, there are surfaces that do absorb various different chemicals. You also have various types of chemical processes that actually take dissolved inorganics and actually precipitate them out into solid form, and then they get deposited on the seafloor. So there are processes like that out there in the ocean as well. Now, sort of into the same category as chemical filtration is what we call a foam fractionator or a protein skimmer. Now, this is used in reef tanks because it's really designed to take out those large organic molecules without using any carbon or any other sort of compound that takes anything else out. And what they do, they're basically columns in which we swirl water with bubbles, and the bubbles eventually start to collect the larger molecules in the top of the column, and we have a collecting container at the top, and it overflows and it becomes, well, let me just say, it's one of the nastier things in aquariums to clean. But there's a good reason for that, because you're getting rid of all that nasty stuff out of the water, and they're very effective and efficient to have. and they are a part of chemical filtration. Now, in the ocean, this does happen naturally. If you've ever been to a body of water, whether it's the ocean or a lake or anything like that, during a very windy period of time where the wind's kind of coming across the surface and towards the seashore, you'll notice a bunch of foam forming sometimes. And that foam is basically protein skimming happening in the natural environment. And if you play with that foam, it's often kind of nasty and smelly. Not quite as concentrated as a protein skimmer in an aquarium, but it's still there. Okay, that is the short version of how aquariums are maintained and how they function. So now I'm going to throw it back to you. How do each of the filter systems that we talked about mimic natural ocean processes? That's going to be your in-depth response for today. And of course, until next time, keep thinking.